Um, so I'm Jared Floyd. I'm a technology strategist in the office of the CTO at Red Hat. And I work on technology strategy around edge computing and edge computing applications such as Internet of Things. What I'll be talking about today is a general overview of what we define edge computing as, what the drivers are, and how Microsoft SQL Server, both SQL Server in containers, SQL Server Edge, as well as SQL Server for big data clusters, fit into this overall strategy. So edge computing, the way we see it, is basically anything that's being done outside the data center. This is a really big category of use cases, but it's anything that's happening outside either compute that's running in a private data center or in the public cloud. That our approach to enterprise applications, to enterprise platforms, has covered those two footprints quite extensively. That you can run platforms that span both private data centers, your private infrastructure, as well as running in any of the major cloud providers. And what we provide in terms of enterprise platforms gives you the same operating system experience, the same container experience, the same middleware and services experience, no matter where you're running the application. So you don't have to rebuild your infrastructure if you're shifting, say, a component from your private data center into Azure or something like ARO, Azure Red Hat OpenShift, which is our containerized platform that's available both for your data center as well as a managed service through a joint offering with Microsoft. So there's a lot of locations that these applications can run, and there's a lot of drivers for doing this. You can think of some of the oldest versions of edge computing, probably the very first would have been content distribution networks, companies like Akamai, where you're moving compute, you're moving data outside your data center because you're worried about bandwidth constraints. So if you had all of your data for something like Netflix streaming from one central data center, you would need enormous pipes going to that data center. They'd be enormously costly. You'd have a lot of transit fees. Instead, what you do with content distribution, you make copies of that data, you put it at different locations in your network, and then you push them out from there. So again, that's very simple, just data-driven, doesn't have a lot of compute involved. The counterpoint for that for inbound data would be, let's say you're building a system of traffic cameras. You have thousands, tens of thousands of traffic cameras, and you want to be looking for things like slowdowns, accidents, anything unusual, I don't know, alien abductions. You just want to know when something unusual is happening. You don't want to have to stream, say, thousands and thousands of video cameras back to your central location, do your data analysis there. Instead, you'd like to do anomaly detection someplace outside of your data center or your public cloud. And so again, that's an edge computing use case. You're taking that data, you're analyzing it either directly at a camera or at a local concentration point, and then you're only sending back the full data stream if something interesting, unusual, different is happening. But you don't want to have to build your applications so that you're building a separate application at each layer in your stack, and instead, you want to have a consistent application that spans that entire distributed environment. So some of the drivers, some of the motivations, reduced latency. You can consider, for example, AR, VR applications where you might have something like a Microsoft HoloLens, and instead of having all your computation happening locally on that device, that'll increase the weight of your VR device, that will reduce the battery life. Instead, you can offload a lot of that computation to, say, a local 5G cell base station. And of course, that's extremely latency sensitive, that you can't send all that processing all the way to your public cloud and back, that you wouldn't have a good interactive experience. Bandwidth, as I talked about, both outbound content distribution networks as well as inbound analysis. Resiliency is a strong driver for delivering edge computing. So let's say you have a retail operation, you have thousands of sites where you're running inventory, you're running point of sale systems, you're running local design applications. If all those depend on your public cloud, then if you have any sort of connectivity issue, suddenly you can't do business at all. And so you want to be able to push those applications, manage them at your local site. Also, you can have data sovereignty requirements that are driving you to have to do all your data processing within, say, the state or the country in which that data is being generated. But there are a lot of challenges as well of trying to deliver applications no longer at your public cloud or private data center. So one of the biggest challenges, you no longer have this illusion of infinite elasticity. You don't have this scale that you have. You don't have the ability to make use of the scalability of compute availability, of storage availability, and of network bandwidth. That you suddenly have environments that are very hostile, both from a physical perspective, that you may not have the same power, you may not have the same cooling, you may not have the same protection against tampering. You may be in a much more hostile network environment as well, where you're not in your data center behind a firewall with a complete IDS to ward off attacks. When you have these distributed applications, depending on where you're putting them, you also may not have people there who know anything about your applications, who know anything about your infrastructure. So you're deploying these systems in environments where you have to have a very quick, scan with a phone and then enroll that system. You may have no trained personnel who can help diagnose issues, and so you need to have and build out a complete system for managing these distributed environments and distributed applications. There are many, many locations that are edge. So again, as I said, we really consider this to be anything outside a data center, be it a private data center or a public cloud. Varies by vertical, but once you go outside your central data center, you could go to a regional data center where you might be running some distributed application. You may have a point that is the transition to your telecom provider, where just over the boundary to where you transition to them, they're providing perhaps some infrastructure as a service that you're running edge applications on. You may be at a 5G base station where that's closer to the customer, but still within the telecommunications infrastructure. You could have a stack of servers that are in a retail environment, in a manufacturing location, where in an industrial location where you're running local copies of applications that can run independently. Or you could even have the device edge, which is something that is an individual device where you might have hundreds of thousands, millions of these, which are connected to individual sensors, actuators, devices. That I'm not considering things that are individual devices as part of this infrastructure. Individual items that might be just running a microcontroller. Those are usually connected via either a local link, like a CAN bus link, or a Bluetooth link, or something similar to a device running a more full-featured operating system. But depending on your application may even span out to those device edge, to those devices and sensors. And so what we see is the opportunity to extend what we consider the open hybrid cloud, which is having applications that span both that public cloud and your private data center, to also extend through all those tiers of the edge. That you can have that same infrastructure, that same application run at any of those locations and provide you a consistent experience from development, management, deployment, and overall application lifecycle. And in any of those locations, you can run some component of SQL Server, either SQL Server in your core, in your edge data centers, or even a component like SQL Server Edge, also available as a containerized application on OpenShift at each of those tiers to aggregate data, to do local analysis, and then to pass that up to your cloud. There are three main topologies that we consider when we're talking about edge computing infrastructure. The first are those distributed clusters. So those are those clusters that are satisfying use cases where you need to have autonomous operation, but these are Kubernetes clusters, OpenShift clusters that allow for completely independent operation of your application infrastructure, completely independent operation of your databases. The remote nodes, which are individual nodes that are connected to a centralized OpenShift cluster. And this is, again, a use case to go with, for example, a 5G radio access network, where you have independent components that are part of your application, but they're centrally maintained, centrally managed, and have consistent, strong connectivity. So these may be either generating data that feeds directly into your central SQL Server instances, or they could be running components of SQL Server Edge and feeding data, aggregating data back up into the data center. And finally, device edge are those hundreds of thousands, millions of independent connected devices that may have intermittent connectivity and have some degree of autonomy and are typically feeding data into your system as well as running autonomous operations in a disconnected way. The place that we see that's really exciting with running SQL Server in these edge environments are that we have the opportunity to deliver not just SQL Server 2019 now as a containerized application on OpenShift, both on premises, in any public cloud, and as a managed service as part of Azure Red Hat OpenShift, but also the ability to deliver both SQL Server Edge, which can do that independent aggregation, as well as big data clusters, which is basically a combination. This is what shows the value in containerized application infrastructure and in using a platform like OpenShift in the cloud, is that big data clusters incorporates more than 20 distinct containers, including Microsoft SQL Server, Hadoop, Apache Spark, Grafana, all these components that allow you to do both data aggregation, normal database operations, and then aggregation, machine learning, model generation, and then overview reporting through a web console. So this gives you that data visualization as well, which you're able to operate, again, as part of your cloud, as well as feeding data in from the edge. And again, this is just an illustration of all the components that are available as part of big data clusters, that you're able to feed in data from any data source. That could be multiple parallel data sources coming in from any of those edge computing environments, that you're able to feed those in, and even from disparate sources, do transformation of that data so that you can feed it into your base master instance of SQL Server, and then do analysis through a whole bunch of different pluggable components for ML modeling, and then visualization across any of your application environments. So I know that's just a really quick overview of our view of edge computing and how it can deliver value across multiple different deployment architectures. But we see that SQL Server in each of these environments has the opportunity to deliver new flexibility and increased performance across deployments that span beyond just private data center and public cloud. So thanks for coming by and listening. I'm going to stick around in case you have any questions about how we see edge computing as driving value to a variety of businesses. Thanks.